All right, let's get right into it. We're always thinking about limits as just temporary problems, things that better tech will eventually solve. But what if there's a limit that no invention, no matter how clever, can ever break? We're not talking about a technological hurdle here. We're talking about a fundamental, unbreakable law of the universe itself. Think about it like this. Just like nothing with mass can ever hit the speed of light, no engine can ever be perfectly efficient. And this isn't a new idea. It applies to everything, from the very first steam engines to the engine in your car, all the way to some crazy theoretical engine you could build at the edge of a black hole. It's a cosmic speed limit, but for converting energy into work. I mean, it seems like it should be possible, right? You put a certain amount of energy in, you get the exact same amount of useful work out. No waste. So why is this beautiful, simple idea totally, completely forbidden by the laws of physics? Well, that's the big question we're going to unpack today. To get our answer, we've got to travel back in time, all the way back to 1824, to a brilliant French engineer named Carnot. Now, what's absolutely wild is that he figured all of this out before the first law of thermodynamics, the whole conservation of energy thing, was even fully nailed down. The guy was playing a whole different game. See, Carnot's big aha moment was realizing that an engine's efficiency has almost nothing to do with what kind of fuel you're burning or how fancy the mechanics are. Nope. The only thing that really matters is the temperature difference between your hot source, what powers it, and the cold place where it dumps its exhaust. That temperature gap, that's everything. So with this insight, Carnot came up with this idea of a perfect engine. And it's not a real machine made of metal and gears. Think of it more as a thought experiment, an elegant four-step dance that physics does, showing us the absolute tippy-top maximum efficiency you can possibly get in this universe. So here's how the dance goes. Step 1, a gas absorbs heat from a hot source, it expands, pushing a piston and doing work. Step 2, you cut it off from the heat and it keeps expanding, using up its own internal energy, which makes it cool down. Now here comes the most important part, step 3. To get the piston back to where it started, you have to compress the gas. And when you do that, you must dump some of that energy as waste heat into a cold environment. It's like a cosmic tax you have to pay. It's non-negotiable. And finally, step 4, you compress it a bit more, which reheats it, and you're ready to start the whole cycle over again. But here's the tragic catch, the real kicker. For this cycle to be absolutely perfect, for it to be 100% reversible and get that maximum efficiency, every single step has to happen infinitely slowly. So yeah, the theoretical Carnot engine is the most efficient engine possible, but it produces exactly 0 power. In the real world, if you actually want your engine to do something, you have to give up some of that perfect efficiency for speed. What's so beautiful about this is that Carnot's whole idea can be boiled down into a really simple and elegant formula. And when you see it, it becomes crystal clear why 100% efficiency isn't just hard, it's mathematically forbidden. And this is it. The efficiency, which we call eta, is equal to 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. And just a quick note, for this to work, the temperatures have to be in Kelvin, which is the absolute temperature scale. So you can see right away, the whole game is about that one little fraction, the ratio of the cold side to the hot side. Okay, so looking at the formula, how could we cheat? How could we get that efficiency to 1 or 100%? Well, the fraction would have to be 0. And there are only 2 ways to do that, and they're both impossible. Option 1, you make your cold exhaust, T cold, equal to absolute 0. Can't do it? The third law of thermodynamics says you can never, ever reach absolute 0. Option 2, you make your hot source, T hot, infinitely hot. Also, yeah, not gonna happen. All matter in the universe would just vaporize into plasma. The laws of physics just won't let you. So for decades, this law seemed ironclad. But then, somebody came up with one of the most famous thought experiments in all of physics. It was basically a plan for a brilliant little heist to steal free energy from the universe and break the second law of thermodynamics. The idea came from the physicist James Clerk Maxwell. He imagined a box full of gas with a tiny little partition in the middle, and manning a tiny door in that partition is a tiny, super intelligent agent, a demon. The question was, could this little demon, just by sorting molecules one by one, break Carnot's law and create a temperature difference from absolutely nothing? So the demon's job sounds pretty simple. It watches the molecules zipping around. When it sees a fast, hot one heading toward the right side, flick, it opens the gate and lets it through. When it sees a slow, cold one heading for the left side, flick, it opens the gate for that one too. Over time, without actually doing any work itself, The daemon sorts all the molecules. The right side of the box gets hotter and the left side gets colder. It looks like it's created order out of chaos, completely for free. It has seemingly cheated the universe. For more than 100 years, this paradox completely stumped the smartest people on the planet. I mean, where's the flaw? How do you stop the demon? And the solution, when it finally showed up, had nothing to do with engines or energy. The bill for this little cosmic heist, it came due in a very, very unexpected place. Turns out, the answer wasn't in thermodynamics at all. It was hiding in the physics of information. The demon's flaw isn't what it does, it's what it has to know. And more importantly, what it has to forget. And this brings us to something called Landauer's principle. And what it says is that erasing information, the act of forgetting something, isn't just some abstract idea. It has a real physical cost. Anytime you delete even one single bit of information from any kind of memory system, you are forced to release a tiny, minimum amount of heat out into the environment. So here it is, the final piece of the puzzle. For the demon to keep sorting molecules, its brain, or its memory, has to keep track of which molecules are going where. Eventually, its memory gets full, so it has to erase what it knows to make room for new information. And that single act of erasing generates more heat and more entropy in the demon's own brain than it ever managed to reduce in the box. The universe always gets its cut. The law is totally unbreakable. And look, this isn't just some abstract theory. It's all around us. It's why diesel engines are more efficient than gasoline engines. They use higher compression to create a hotter T-hot. It's why massive power plants are always built next to rivers or oceans. They need a huge stable T-cold to dump all that waste heat into. And NASA even uses these super efficient engines called Stirling engines, which are some of the closest real-world machines we have to Carnot's perfect cycle, to power their equipment out in space. Just take a second and let that date sink in. 1824. Almost 200 years ago, before we even really knew what energy was, Saudi Carnot understood its ultimate unbreakable limit. And the reach of this law is it's truly cosmic. Stephen Hawking's work showed us that even black holes have to play by these rules. They have a temperature and they have to radiate heat away, something we now call Hawking radiation. And that's just a mind-bending thought, right? The exact same fundamental principle that governs a clunky old steam engine also governs the most extreme and mysterious objects in the entire universe. Carnot's law isn't just a rule for building better engines, it is literally woven into the fabric of reality itself.